Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We got our sorting kind of, I don't really want to use the word working, but it kind of was working yesterday. And we had some visualizations that we did to sort of see what was going on, and it's starting to look respectable. So at this point, I'm not 100% sure what the best course of action is because we kind of have two things that we've got to do. One thing that we have to do is we have to go ahead and put our sprites into layers like we were in the middle of doing when we kind of went over and took care of the sort. So we've got to deal with that. The other thing that we have to do is we have to figure out what our solution is to the n-squared sorting problem, because I don't think that's going to be a long-term viable thing to have in there. I mean, computers are ridiculously fast, so somehow it's running at a reasonable frame rate right now, but it's kind of ridiculous that it is. I'm rather surprised at that. And so, in general, we don't want to have this sort of thing at the core of our render loop that has to be doing n-squared stuff. It just doesn't seem like a very good idea, to say the very least. So, it's a little bit warm in the hoodie, I'll be honest. I may not be able to keep the hoodie on for the entire stream, but what are we going to do? Temperatures, they fluctuate. So this is it, day 309 on Handmade Hero. Day 308 is the code you would want to start with if you're trying to match up with what I'm doing. That's the source code that I'm starting with now. And if I go ahead and open up our project here, let's go ahead and compile that. And I'm going to go ahead and get MSDev going as well. If you remember where we left off, we had it to the point where it seemed like the sorting was actually working pretty darn well. And we kind of have some ridiculous, information overlay stuff happening here. We can turn that off pretty easily, and I probably should turn that off now. That's this global show sort groups thing. Because at the moment, I'm not sure that we're going to be focusing on the sort group debugging or anything like that. So this is what things look like at the moment. And actually, like I said before, I think they look pretty good. We have a couple things that we have to address, but most of them seem, actually fairly logical and don't seem to implicate that the sort is performing incorrectly. In fact, the sort seems to be performing really quite well, considering what I'm feeding it right now, which is not particularly good data by any stretch of the imagination. So, a couple of things we have to deal with, and I'm not exactly sure how we want to deal with them, but for example, in this situation here where we're going to be hopping up things, we're going to have to think about what we want to do there, because our z values are kind of all wrong in this case, and we're going to have to try and make it so that the y sprites can sort of hop over things correctly and stuff like that. And we still have some other issues here to take a look at. You can see there when you get like that guy hopping up in there, you can see how we kind of get some bugs when you get sort groups. I think those have to do with cycles, I'm not sure. We also currently have those sort of highlighting reticles on, which are not super useful either in terms of adding more complexity to the sort, which is not something we actually wanted to do. But let me see where that actually ended up. That's in world mode. So yeah, where we're drawing those volumes, those collision volumes. I don't actually know where we're drawing those collision volumes. We're creating a bunch of collision volumes. I always forget this because we kind of did this and then we weren't working on the entity code for a while. I forgot I moved things into entity. I'm like, where is the code? The code's right there. It's just in a different file. Yeah, it's getting too hot in here. We're gonna have to lose the hoodie. All right, the hoodie has been retired temporarily. So yeah, so this is what we look like here when we don't have those extra sprites. And you can see that like some of the bugs that were happening on the left side of the screen don't happen when those extra sprites aren't in there, right? And so, I feel like the sorting routine seems to be working relatively well at this point, and we have to be sort of conscientious and think about it going forwards, just from the standpoint of we got to make sure that we start putting in good data and don't ask it to do things which it can't do, because inherently, like I said at the outset of this, we are sort of inherently asking it to do something that is not particularly stable. We're asking it to do sorts that have no real solution. So it's kind of a situation where we're just using some fuzzy stuff to produce a sort that we hope will give us pleasant results. And for the most part, in a lot of these cases, it's working. So I feel like that's a good start for us. It's something we'll have to revisit once we sort of have everything in here that we want to draw and can get a little bit more visibility on it. But for the moment, I'm relatively happy with it. So the thing that I am more interested in doing at this point, since now we have something there, is a making sure we have some sane idea of how to get the n squared stuff working properly, right? And then the other thing that we have to do is figure out how we're going to do our layering, because that's what we were right in the middle of doing. And that's another tricky problem in and of itself, and the reason for that is just because we kind of want this orthographic view, but then we sort of have this hybrid kind of perspective concept, which is that as we go up, things do in fact shrink, right? So although we don't want this sort of left, this rightward leaning thing to be happening, we do want to be able to have, as we sort of come up through other levels of the game like that, we do want the ability for the floor to kind of shrink down, right? And, we could decide to abandon that. We could decide not to keep that, just to keep the perspective more constant. But I felt like it was just kind of a really neat effect that happened. And so I'm just sort of the opinion that I would like to try to preserve it as long as possible until I see something that really makes me go, no, there's really just no way we can possibly keep this. It's awful. Right? And, certainly if we were trying to make it as easy as possible for ourselves, we wouldn't do that. But, at the moment, that isn't the primary goal, right? So, given that, what I think I would like to do first is I think I'd like to take a minute to sort of look at this n squared situation, right? And, so like I said, we got two problems. One is that we don't, like, the sort rule that we have in there can't handle layered things on top of each other. And it's because it's kind of using hacked ideas about how to sort things that are entirely based on, like, what will look nice for a normal room, right? So we need to separate things into layers, and that'll fix our debug overlay as well, because like right now our debug overlay gets blocked by Y sprites, right? And that's, according to the rule, that's actually what should happen. But in addition to that, I would like to figure out how to make sure that build sprite graph doesn't take a huge amount of time. And fortunately, we can easily force it to by just dumping tons of sprites on it, right? That's the whole point about the n squared situation. Here there's just not enough rectangles on the screen, not enough sprites on the screen to blow past the frame budget. So even though we're doing an n squared algorithm for the sorting, we're just not feeling it, and that's just because computers are crazy fast. Even though this computer's from 6 years ago at this point, it's still so fast that it's just like, yeah, no, don't worry about it, right? But if I just drastically increase the number of sprites by opening the debug view, right, all of those are still going through the sort, you can now see that build sprite graph is taking a massive amount of time. And that's, of course, because there's so many things that it has to sort that, you finally start to see that n squared actually matter. And so I want to, I think today, just figure out something we can do about that. I think that's probably the best use of our time. Okay. So, let's take a look here. So, essentially the problem that we have, and here's the day marker. day 309. Essentially, the problem that we have, is we've got some series of rectangles on the screen, and we need to know which ones overlap, right? We're trying to figure out all the sprites that overlap each other on the screen. And at the moment, we are just doing that by checking all sprites against each other in an n-squared fashion. So if there are 5 sprites, we will check each sprite against each other sprite, and we do that by having 2 nested for loops. So that's what's happening at the moment. Now, the problem with that, obviously, is that as the number grows, we are going to be doing an n-squared number of comparisons. Now, you remember when we talked about O(n) squared, right? If you consider the number of things here to be n, then if I have to compare each thing with each other thing, I end up with doing n things n versus n things, or n squared. It's a very simple idea, right? And of course, it's pairwise, so we don't need to compare if we have like A and B, right? We don't need to compare A versus B and then B versus A. So we're not doing all n-squared comparisons. We're only doing sort of like half of the n-squared comparisons, right? Because we don't have to do the backwards version of each one. But it's still proportional to n squared, right? If you take n squared and you divide it by 2 or something like that, it still grows compared to n squared. It's still a graph that looks like that, and just because you've flattened that graph out a little bit doesn't change the fact that it, has this really bad growth curve where at some point you're going to get up into this really steep, intractable problem space. So what we'd like to do is figure out a simpler way to build this graph. And, you can imagine some pretty straightforward ways that we might be able to do this. But, this is kind of a classic computational geometry. Well, I don't know if I want to call it computational geometry. This is a classic geometry problem. And there's a lot of different ways that people go about doing it. The way that I tend to go about doing it, because it tends to be easiest, is I tend to just bucket things. Right? So what I will do is I'll say, well, okay, if I've got a screen's worth of sprites and I'm trying to figure out which ones of them overlap, I'm just going to go ahead and say, well, let's make some buckets here, and we'll just sort inside each, well, not sort inside each bucket. We'll just say, when we're going to test somebody, we only test them against sprites that are in the buckets that they overlap. If that makes sense. Now, this doesn't solve the n-squared nature of the problem in any real sense, right? Because it's still n squared inside the bucket. But what it does is it truncates the n down so it's always a fairly small number, which means you never get up into that bad part of the n squared curve. Right? Now, it's possible that we could do this in non-n squared fashion, I believe. I'm not a computational geometry kind of a person, to be honest with you. It's not, my strongest suit. But my recollection from that literature is that we could actually do this without needing to do it n squared. And the reason that I say that is because one of the things about overlap testing is that every test that you perform gives you information about what other tests you may or may not have to perform, right? And, to give an example of that, I'll give a very simplified example of that. Suppose we were going to test for overlap in just one dimension. So this is one-dimensional overlap, right? Well, if I have some spans, and, let me try to draw them in some way that makes sense. So if I have some spans here, right, and I want to know if these things overlap, immediately you can start to think of, well, I could sort these spans by like their minimum coordinate, let's say, or something, right? And I know that sorting is n log n. I know that I don't have to do n squared to sort something. So I could do an n log n sort of these things first, and then actually have them in order. And once I have them in order, I know that I only need to test the next person in the list to see whether or not I overlap with them. Because if I don't overlap with them, I don't need to test anybody further down the list, right? So at some level, you can start to see how computational geometers could easily build algorithms based on n log n sorting in various axes that would allow them to reduce the number of tests that they need to do in order to figure out what all the overlaps are. And I believe, if I'm not mistaken, that you can sort of do literally what I'm talking about here in a 2D arena as well. You can first sort by one axis and get, things in that axis, and then you can do sorts by another axis inside, a stable sort inside that axis by another axis, and then end up with a thing where you can sort of only do the checks that you want to do. Now, like I said, I don't know that I want to do that. And the reason that I don't know if I want to do that is because although that's going to probably be the more theoretically fast thing, in the sense that it could scale to the highest number of possible objects in all scenarios, I don't know that that's going to actually give us the fastest results in practice, because in practice, we're not going to have more than 1,000 sprites in a little section of the screen, right? And so I feel like, a method where we dice things up is really going to probably be a more efficient thing for us to do in the long run. And it's probably going to fit our usage better. So that's my assumption. Now, I don't know that that's true, but that's just what I would assume. So that's my inclination. That's what I would go with if it were up to me for figuring out, what the overlap is. And when I'm thinking about this, I think the primary complexity there, the primary sort of set of decisions we have to make is how are we storing this information, and how are we actually going to do the bucketing, because there's a couple different ways that we might want to do it, right? So, if you imagine that I have some kind of a grid, there's a lot of ways we can go about spatially partitioning things so that we can reduce the number of checks we have to do for rectangles. So, if this is a rectangle here, and this is a rectangle here, and then there's another rectangle over here, maybe we want to check these two rectangles for intersection because they're sort of occupying the same general space, and we think they might overlap. They don't, but we think they might. But we definitely don't want to test this against this because they're nowhere near each other, and we don't really probably want to test this against this either because they share, they're divided by one of these lines. So, if you think about sort of narrowing testing in this way, like a spatial partition, so-called because we are partitioning space up into different regions for some purpose. If you look at what's implied here, there's more than one way we can choose to represent this, or there's a number of ways we could choose to attack this problem. And the underlying sort of element in how we're going to make, or what makes there be decisions to make, the underlying, I'm trying to think of what the word is. We have choices, and the reason we have to make these choices, let's put it that way, is because things don't always fall within a bucket, right? So if things always fell entirely inside one whole bucket, always, then we wouldn't have to think, really. We'd just be like, all right, well, we make some number of buckets, and then really all we have to figure out is how we're going to store the fact that stuff's in a bucket. That's the only decision we have to make, is how to store. But because things like, for example, this rectangle right here span 4 actual spatial buckets, if the way we chose to represent this was, well, we need 4 We need to say that this thing's in 4 different buckets so that when someone looks up in it, it knows that this guy's there, right? We have to start thinking about how are we going to handle that activity, right? So one way to handle that activity is to break up each thing that we store and store a record of it in each bucket that it touches, right? Then when we go to query, we can say, okay, all the buckets that I touch, look to see what all the things are in those buckets and test against them, right? We can certainly do that. Not a huge deal, but again, it's a decision. Another thing we can do is we can create a more hierarchical notion of what the space actually looks like and avoid breaking things up in that fashion. And let me give you an example of how that sort of works. So suppose I was to take, well, I'll try to stay with this example, I guess. Suppose I was to take this entire section here and say that I have sort of a top-level region that's the entire area. So anything that overlaps with it could be stored in this. Okay? Because all these things are obviously within this rectangle. And then I say I want to divide it in half. Right? I'm going to just divide it. Well, once I divide it in half, now there's some things on one half and some things on another half, right? And I only need to test, each half. If something's in this half, I test this half. If something's in this half, I test that half. That's all I really need to do, right? Then I could go ahead and divide it in half again, let's say, right? Maybe I divide it in half again, and of course, unfortunately, I didn't really draw a halves line here, but let's say that I was going to do it in half again, and so it'd be something like that. And now we get to the first place where I'm sort of saying there could be a difference in here, right? This rectangle overlaps the split point where I'm going to divide it. And so if we were to follow the same general pattern in the grid-based method where we just store it everywhere that it appears, nothing really changes. I'd store it in either side, right? I'd have a copy, a record that it was in both of these sides, and I'd move on. But I could instead decide to not store it in that lower split level and instead store it at a higher split level, right? Because if you think about what this ends up creating is it sort of says, well, I have this giant region here, right? And then I split it into 2 regions. I split it into a region that was just the stuff on this side and a region that was just the stuff on the other side, right? And then I took, these 2 regions as well, and I split them again. I said, well, now I've got one that's like, well, it's just the stuff that's like up in there, and just the stuff that's down in there. And the same thing would be true in this case. Right? So if you look at what's going on there, you can kind of see what I mean now when I say we have a choice of where to store things. If we want to, we could store things in whatever bucket doesn't split them. So this guy cannot be stored in either here or here, but he could be stored in here. So he would be stored in here. Now, when we do testing on somebody, we do the exact same process, and we just test against everyone in everything we would have traversed in order to find their location. Right? So that's another way we can do it. This method of doing splits, there's a lot of different things that you see. If you've ever seen like quad tree or KD tree, right? BSP tree. All of these things are just different kinds of spatial partitions. A quad tree is one that always splits it into 4s, right? It's this kind of a process. A KD tree is one that always splits exactly one of the orthogonal axes every time, but only one, right? So it might split this into 2 halves, and then it'll split this into 2 halves, but it's never going to produce 4 things. It's only going to split 2, so it's basically like a binary tree. A BSP tree is very much the same as a KD tree, only instead of picking cardinal axes, a BSP tree can pick anything. So it could like split that way if it wanted to, right? And so, you know, the KD tree is kind of, you might think of it as a sort of more restrictive subset of a BSP tree. Like a KD tree still is a binary space partition. It's just one that can only pick one of the cardinal axes as it's split. So the thing about a lot of these, and you know, I don't have anything against these guys. They're all typically just fine. Is, you know, really, you don't get very much for doing this stuff. Typically, the only time that I find that it's really all that great to go with something more complicated like this, where you've got something, you know, more complicated than a simple grid, is if you have level of detail concerns. Because you can understand why having sort of things that split into smaller pieces and then could be collapsed upward, if I had level of detail stuff going on here where I'm like, oh, you know, I'm looking out across this thing, like I'm standing here and I'm looking this way, so I might want this to be at a low level of detail and this to be at a high level of detail. You know, these partitioning things tend to make more sense to me in those kind of contexts where you're not dealing with a uniform density, uniform access kind of a thing. But that's not really what we have. You know, we know we're looking at a flat, bounded region where everything is the same level of detail, and we're equally likely to have sprites on the left side of the screen and the right side of the screen. There's not going to be like a drastic difference there. And so my suspicion is a lot of this stuff would just be wasting a lot of implementation time doing fancy things that we don't really care about. So my assumption is that what we probably would want to do, the most efficacious thing for us, would be to figure out how to use a very simple grid bucketing scheme, probably that stores things multiple times if they cover multiple things, is probably the most efficacious thing that we could do. That's my guess anyway. And the reason I say that is because I don't see us getting any real benefit from any of the other schemes. Now, it's possible that something more sort-wise would actually be clever. Like I said, you know, we've kind of got these other options here. And so, you know, if we wanted to spend a lot of time on it, I could see this being something where you would investigate and say, okay, let's take a look and think about, do we believe that, you know, we could get a good, clean way of testing for rectangular overlap here with a nice computational geometry algorithm, you know, that doesn't require a lot of code and doesn't look like it's going to be too computationally intensive for what we actually want. You know, maybe you can do something much more efficient there. I'm not sure. But I think for the time being, this is probably more what I would say makes sense. And furthermore, what I'd say is, if we look at this sort of grid system, you know, one thing that you might say is, well, you know, what if we have some giant sprite here that's covering all these things? You know, we're going to be adding it to all of these buckets, and it's just going to be a nightmare, and that's just, you know, right? But what I would point out in this case is that we're under no obligation to use the grid, because we can always have a sideband of things that we compare against in addition to the grid. So what we can do, if we want to, is just make it so that when things are roughly grid-sized or smaller, we put them in the grid, but when they're like larger than, you know, 4 grid squares big, we can just leave them in a linear array for testing, because there won't be that many of them. So we can avoid sort of pathological cases where some giant, you know, cloud sprite is being glid over the screen. If everyone has to test against it anyway, we don't need to go through the grid to divide it up, right? So that's, you know, sort of that's a way that we can prevent certain pathologically bad things from the of the grid from happening, because we kind of know our use case, and we know that that's, you know, something we can easily just put as a sideband. So yeah. So if you look at what's going on at the moment, you can kind of see that, you know, if I open up the profile here, right, you know, it's debug mode, so yeah, we can go compile and release mode and it gets a lot faster. But if you take a look at that, you can see that if we open up the debug view and get all those sprites in there, I mean, look at how expensive. It's just crazy expensive, right? Really, really, really expensive to do that build sprite graph. So, you know, what we want to look at here is, can we go implement sort of a simple grid thing that would break that down and make it so that it's not 93%, you know, get it down to something more reasonable, and so we're not afraid that it's going to break as we move forwards. And it doesn't have to be the best thing, right? Like I said, we don't have to do the best possible thing here. We're not trying to be too prematurely optimization oriented or anything like that, but we just need something that we can feel comfortable with, so like we open up the debug window, we won't have a giant disaster. And yeah, you know, the other way we could approach that is say, don't bother optimizing this, just go turn off the debug view and let it be unsquared. I don't know. I think we should just take this opportunity to optimize it, because you know, it's obviously slow, and obviously we have good, not super expensive ways we can go in, and I mean expensive in terms of code, ways we can go in and start to attack that. So I think we want to just give a little bit of a try there, even at this stage. So, you know, luckily for us, this is an optimizer's dream scenario, obviously. We know all our time is spent here. So we know that really all we have to do is accelerate this function, right? We just have to accelerate these checks. So there's really not much mystery to it, so that's a good thing. And we know that really all we need to do to produce the correct information here is you know, make sure that we always at least check all rectangles that might intersect, right? So right now we're checking all pairs of rectangles, and we just want to say, okay, can we winnow down that number to a small number that get tested against each other? And as long as we do that, we think we'll be fine. Okay. So how are we going to do that? Okay. So I'm going to start with something fairly stupid. And we're going to go from there and see how the fairly stupid thing holds up. And we'll get more complicated as necessary. So here we are in build sprite graph. And I'm going to say that we have that sort of grid, like I just sort of talked about. I'm going to say we have a grid. And inside that grid, I guess I'm going to store... in fact, I guess I have. I've got these sprite bounds, right? And so, yeah. I think I'm just going to make a temporary little structure here, and I'm going to say that this is our sort grid, our sort grid cell. Oops. And inside the sort grid cell, I guess I don't really need it to be called a sort grid cell. I guess I want it to be called a sort grid entry, really. I'm going to use a simple chain here. And you know, every time I do a linked list, people get concerned because they're worried about cache effects. I think it's great they're worried about cache effects. That's totally fine. Remember, though, these are all coming from the same memory unit, so they're packed close together. And it's usually not such a great idea to worry about something like cache effects, so you know you actually have them and that you care, right? So I'm going to write the simplest thing first, and we'll see how it performs. And then, you know, the time to worry about cache effects is usually when you actually start seeing that you're having performance problems and that they're due to cache effects, right? So anyway, so I'm going to do a sort grid entry here. The sort grid entry is going to be, yes, quite cache unfriendly to say the least, because of slightly the next pointer, but they're going to be packed together, so that's really not going to be that bad. But also because we're sort of out-referencing, right? We're saying we're going to reference sprite bounds that are out kind of in a, you know, in another, I don't want to use the word part of town, but we're sort of saying there's a thing that's elsewhere, right? So we've got our sort sprite bound here, and we're going to say that that sort sprite bound is the thing that's in this cell. So it's like an occupant. And now I'm just going to say, well, all right, let's make some of these sort grid entries, and I'll make a pound define here that's like you know, sort grid width and sort grid height. you know, or something like this. And let's just start out by saying it's 16 by 16, and I'm not picking that number for any reason other than I'm just going to test it. And, you know, I guess now that I think about it, well, we're typically sorting a 16 by 9 screen, so let's do 16 by 9. And so I just need some numbers to put in there. So here's the grid, and we've got the sort grid height and the sort grid width, and I'm doing these in backwards order at the moment. Because we'll probably, well, I guess, you know what? I could do them in same. There's really no reason not to. So now it's XY addressing for this grid. Okay? So what I want to do is I want to initialize this thing to 0 and say there are no occupants in it, right? So there's nothing in the grid at the moment. It's empty. I'll compile that to make sure we're all good. And now what I want to do is I want to do a pass over all of the input nodes that we have. Like so. So I want to do a pass over all the nodes, and for every node that we have, I need to put it into the grid everywhere where it currently exists, right? So, you know, I've got to say, like, okay, it's basically a for loop inside the loop where I'm saying I have to touch all of the grid squares that this square might touch, and I need to record the fact that this sort grid entry is in there. So in here I've got sort of my grid X. And I guess I shouldn't put 0. This is something. And similarly, I've got my grid Y. We don't know what these numbers are. We're going to have to compute them. But for each one of those, so for every grid square that I'm touching, I'm going to put a record in there of my existence. So I'm going to do a sort grid entry. Entry equals push struct sort grid entry. And for each one of these, I'm going to say that its next equals exactly what you expect its next to be, and its occupant equals me, right? So this is just going to be grid X, grid Y. And then I'm going to go ahead and say that the thing in that position is me. So that creates basically a chain, and so now in every grid square, there's now a chain of all of the sprite bounds that are, you know, in that grid square, right? And that's that. So one of the interesting things about this that you probably can already see is now that I'm doing it this way, it's unclear that we really need to do sort of a separate pairwise check, right? Because look at what's going to happen here. Every time I come in here to add one of these guys, well, I could just check against all the people that are in the grid right now, in this grid square, right? I could just check against them and be done, right? I mean, in theory, anyway. Sorry. Got an itch there. Right, so I don't necessarily have to do this in 2 passes where I kind of then do my n squared loop over the thing. I could instead just do the checking right here and add the edges at this time. And I'll say, obviously, there's kind of, if you're kind of paying attention at this point, you probably also are starting to think, wait a minute, isn't there another thing we can do? And you would be correct about that, but we'll kind of get to that a little bit later. Okay. So, and I suppose one thing that might be true about this is at the moment, since we're using the indices here, the index we're using node indices, I might have to say that instead of doing it this way, I might have to say that it's the occupant index. Now, I don't know if that's going to be the most efficient way to do this, but it's just how the rest of the code's written. So for at the moment, I'm going to say that's the way we're going to do it, just for the moment. All right, so if I was to do this, now I've got all these grid squares, and I need some way of actually affecting the sort. I want to jump ahead and say, if we take a look at what happens on recursive front to back here, what we could do is say, well, we've got this first edge, you know, walking thing here that's going through all of the edges that are coming out of me. I want to know all the edges that have me as the frontmost person, right? But we could just do that test. We could just do this test directly and never actually save that result at all, right? Meaning we don't have to actually create the edges of this graph. I did it sort of to show how that works and to do the graph algorithm as a graph algorithm. But there really isn't any particular reason to save those edges. They don't really do any good because we only check each person one time. And we mark them as visited and we're never going to look at them again. So we could just at that point take that person and test them against everything, right? If we wanted to. We could just do that, just right then. What I would say about that is, you know, maybe that's a good reason to sort of say, you know, right inside here, we could actually do that graph walk. We could do that graph walk sort of directly by just testing the grid. I don't know if I'm probably not explaining this very well. But I'm just trying to say, instead of doing this pass and creating the edges, we could instead also just do this, where replace this function, this part of the function, with just an iteration over the grid that this guy, you know, whichever one we're picked here, do an iteration over the grid that this guy's on and do the front to back that way, right? So yeah. I think that's reasonable. All right, so let's take a look here at this, though, because there's another thing we actually need to do, which is the grid X span situation. We need to actually sort of compute that stuff. So this is sort grid span, I'm going to call it, which is I'm just going to figure out a way to compute these numbers here. So this is like a min X, min Y. Well, you know what? We already have this. It's a rectangle 2i, isn't it? So this guy right here is exactly what we want. A min X, a min Y, a max X, a max Y. So we need something that's essentially going to tell us, hey, I need you to give us the span for this screen space rectangle. So this is like get grid span, and it's going to take a rectangle 2. That's just the screen area, right? And it's going to return a result here that we don't know what it is. But then once we do that, we can say, okay, here's the rectangle 2i. This is the grid span. We're going to say get grid span. And we're going to say for the screen area of the sprite bound that we're on. And we're going to take min x, span max x. And I'm assuming that probably if it's max x, we should do greater, like less than or equal to, because that's probably the more sensical linguistic interpretation there. So it's probably the least likely to be confusing and have errors about what people think is included and what it's not, right? And so, yeah. I would also like to put some assertions here on our calculations to make sure that they're not completely bogus. Well, actually, I guess the assertions probably aren't what we're going to need. We're probably going to want clipping, right? So we're probably going to want to say that if result min x is less than 0, you know, and maybe I'll do it this way. Same thing here. So this way, the coordinates are all going to be clipped. So there you go. So this is basically just a thing to make sure that, you know, we're always inside the grid. After we're done. Now, I guess there's a slight other thing here that we might want to do, which is, you know, maybe we want to do this. And the reason that I say that is because we may want to return a bool here, which is this thing even in the grid at all? Because if we find that this thing is outside of the screen area entirely, then we really don't have any reason to process it, right? So you might argue that this makes a lot more sense as a code structure, because we're going to say, well, if this thing comes back and tells us there is no real, you know, this thing's off the edges of the screen, well, we don't need to sort it anymore because, I mean, who cares, right? Just discard it. It doesn't matter. Now, that's not 100% true. So because this is a topological sort, we might get into situations where something off screen, going off the screen, changes the topological sort and you get some kind of a pop. But my expectation would be that if that was true, we probably have a problem with the sort anyway, because, you know, if it's not producing a stable sort in that situation, we're probably going to have to adjust the rule for other reasons. Now, don't know that that's true. We'll see. If it turns out it's pretty easy for us to get rid of that, that discard if it turns out that that's not true, right? All right. So here's the grid X, grid Y testing. And my assumption is that as we come through here, like I said, we could probably just do the edge adding right here. Now, there is a little bit of a downside to this, and I'm not sure exactly how to... I'm not sure exactly how I want to deal with this, but I suspect that I will need a generation number here. And the reason that I suspect I'll need a generation number or something if I was to do it, this is why I was sort of saying I'd like to do it out here instead, is because there would be nothing from because I'm doing this per grid cell, there'd be nothing stopping me from adding multiple edges. Well, you know what? I guess it doesn't matter if I add multiple edges. If I add multiple edges, it doesn't matter because it'll get cleaned up in this pass. Let me try to be a little bit less out in my head on that. So let's say I've got a situation that looks like this. Right? Here is a rectangle, and here is another rectangle. Now, obviously, these two rectangles overlap. Let's call this one A. Let's call this one B. So obviously, we want an A, you know, in front of. It's in front of B. So we want to add that edge. But if you look at what's going to happen here, we're going to be looking at it from the perspective of grid cells for testing. And so what we're going to see is we're going to see B twice when we iterate through, and we'll add, if we just did naive testing, we would end up adding it. When we did this cell's tests, we'd add it one time, and when we do this cell's test, we'd add it one time. And we end up with two edges to the same node. But, like I was saying, I guess it doesn't matter because it gets cleaned up in this phase. Because here we already would have visited it, so we wouldn't test it, and we'd be fine. Now, one problem with it is I think it would think everything was a cycle all the time. So it would kind of break our cycle testing. And I don't really know what we would do about that. Since we don't super care about the cycle testing, I'm not sure how much that matters. But if we needed to start breaking cycles intelligently, it might. And so the problem that I see here is just figuring out, well, okay, if I didn't want to do that, how would I make sure that I only ever test this against test this pair one time, even if I encounter the same one in multiple grid squares, right? And in order to do that, I would need, like I said, some kind of a generation number to prevent me from doing that test ad infinitum. And so we could do that, or we could not do that. I don't know. We'll see in a second whether we want to do that or not. It doesn't affect the algorithm one way or the other, but it affects whether we can do the cycle testing in the way that I was doing it. And so, you know, we'll consider it. It's a pretty easy change to make. So here we are with our sort of our bucketing there. And, you know, in the get grid span call, obviously, I've got this result rectangle coming in. And what I need to do for this result rectangle is I need to sort of, now I need to bin the screen area that's coming in versus the total screen area. So I guess we would say this is, maybe I'll call this the source and this the desk. So what we need to do is figure out a way of getting the source into those buckets. Now, we've done this before, right? This is a truncation kind of a process, right? And we need one more piece of information in order to do it, which is going to be, how do we know how big the actual cells are, right? So we need something here that's going to be like a V2, which is our cell dim, however big the grid, you know, cells are. But once we know how big the cells are, it's a pretty straightforward computation for us. Like I said, we've done it many times before. All we have to do is take one of the source inputs, right? Like get min corner of the source. So if we were to look at what the minimum corner was, and we want to figure out where that is in our cell space, we just have to do a multiplication by whatever the inverse of that cell, like we want to divide by the cell dim, right? Now we don't want to compute that inverse every time probably. I mean, although these days divides are cheap, we probably just could. But you know, let's say we pre-inverted it, so we're just going to do an inverse cell dim times the min corner. In this case, it's a Hadamard product because we actually want to multiply, you know, the x by the x and the y by the y. But that gives us back what's going to be our actual min value. This is like our min in float space, right? And the same would be true for the max. The exact same process would give us our max corner where that is inside the grid. Once I have the min and the max that I'm going to use for the grid, now it's a simple matter of taking those and truncating them down to make whatever the actual integer value is that they would go in for the grid, right? So now I'm just going to say, well, okay, my destination min x is just the min r's x, and we're just truncating this down. So this is a truncate down, and in each case, you know, it's pretty darn straightforward, right? So that's really it. And so what I need to do now is I just need to have my inverse cell dimension there. I need to figure out what that's actually going to be. That inverse cell dimension is just going to be, you know, 1 over, it's just going to be 1 over whatever the cell dims actually are. And so all I need to figure out in order to finish is I need to figure out, ooh, running out of time. I need to figure out what is the dimension of one of these grid cells. Well, I would need to know the screen area, but if I knew the screen area, so like if I knew the screen width in pixels, right, or whatever it is, it actually doesn't even really matter, but whatever the demarcation is of the screen that these nodes are coming in. I just need to take whatever that screen width is, divide it by the number of these cells that I have, right? And that's going to give me the actual value that I need. Now, if you see what happens there, I've got this divide, and I'm immediately going to invert it. If I want to, I can just do the divide the other way around first time out and have my inverse cell dim directly. And that's probably a easier thing to do, right? All right, so let's take a look at this. Oops. Oops. And see, can we get the information that we actually need here, right? Because when we do the build sprite graph and we have the game render command stuff happening here, I need some way of getting that information about the size of the screen, right? Which I don't know that we actually have yet. So let's see. Hey, look, we've got width and height, and I think that's all we need. So what that means is when I call my function here, I should be able to just pass it screen width and screen height. Those should be casted certainly. And that's easy peasy. Okay. So if I go to commands width and commands height, I build it. And let's see what else we got here. Syntax error, get grid span. Oops, I think we only have B32s here. And I agree with that. So what we want to do here is have a B32 that's like inside. Equals something. Okay. So this is a little bit sloppy here, but what we need to do is just go, okay, we want to know whether this thing is entirely outside of the screen area, like completely, right? And now I think about it, maybe this was all kind of stupid, although, well, no, I don't know, because I kind of want that to be a uniform function. But what I was thinking is, well, we need to know the screen width and the screen height in order for it to do the rejection, which means I would need to pass those as well to get grid span, which is kind of a pain, right? It would be nice if it was a little cleaner than that, but what are you going to do? So if I want to test here to see whether this is actually inside or not, what I could do is right here just say, like, if rectangles intersect and have, like, screen area and or screen total screen, something like that, and source, right? And if they intersect, then it's inside. And in fact, I could actually do it this way. And then I could just pass a rectangle that was the screen rectangle, right? That's certainly plausible. And if I want to do that, I'd just say, like, all right, I've got a rectangle here. It's a total screen rectangle. It's a rect min max kind of a situation. The min is just going to be 0, 0, and the max is going to be, screen width, screen height. Okay. So, yeah. Oops, that's supposed to be rectangle too. What are you complaining about, sir? Sir? I see what you are complaining about. You are complaining about those, which are not supposed to be there. Okay. So getGridSpan now kind of has some stuff it's got to take. It's got to take the total screen. It's got to take the inverse cell dim. It's got to take the screen area, and then it's got to take the destination. Not a huge deal. These are S32s, I guess. And this requires an arena. And I think this is occupant index. But I believe, just in time for the Q&A, I believe we now are bucketing. So yeah, we haven't quite gotten to the point where we're actually using it for acceleration. So now we're kind of just bucketing, and we're not actually doing anything with the buckets, but that can be tomorrow's job. It's Q&A time. The Mic DX. Using the grid system, do you think that would be good to use for pixel perfect collision? Yeah, I mean, pixel perfect collision is actually not really related, I guess is what I would say. Let me try to explain why it's not. So, you know, fundamentally speaking, you've got some sprites, right? And what you want to know is, do these two things intersect? And if I want to know whether the pixels of them actually intersect, well, obviously the first question is, do the rectangles intersect? Because you would never start testing the pixels if you hadn't tested the rectangles themselves, right? So once I determine that these two rectangles intersect, then I have to look at the pixels in these two sub-rectangles of each sprite, right? And that is a separate pixel test. So I have to do the rect test, and then I have to do the pixel test. So we're doing this stage. It doesn't matter whether this stage is happening or not, right? It's completely unrelated. It's just something you would do extra if you wanted to do pixel accurate testing. And furthermore, what you'd probably have to do if you wanted it to be fast is you'd probably have to break these up into blocks that said whether there was stuff in them maybe, so you didn't have to check every pixel if you were doing a high resolution. So you'd probably need to do some sort of grid-based encoding of your sprite as well. But really, the grid-based binning, it doesn't have any, whether you were doing a pixel test or a rect test, you're always going to test the rectangles first, and it doesn't matter what you're doing down the line from that. It's the same at this point either way. So whether you decide to use a pixel test or not, you wouldn't really care, I don't think, about the implementation at this level. Would be the same in both cases, would be my guess. The Sizik, why not have the debug overlay rendered to a separate layer and have it draw in the order submitted instead of wasting time sorting? Yeah, I'm not opposed to that. Like I said, that was exactly, I think, quite literally what I said when I was pointing that out. But the reason was because I know we're going to have a lot of sprites. The debug system now is the best stress test because it happens to have a ton of sprites. So since I just wanted to do this anyway, I want to make sure it's fast enough. I don't think there's any point in doing that for the debug layer because I think this will be plenty fast enough, right? What I'm about to do I think will be fine. And so at that point, I'd just be wasting time if I also did some other solution to make sure the debug layer didn't have to go through the sort. Because I want the sort to be fast enough for that. Isaac, I think a sort-free mode would work well with the cutscene as well. Well, but the cutscene works well with the sort mode, though. So we don't really need to have like different modes if there's no reason for them, right? Any other programming questions from today? Mrs. Streaming again today. Why do you not use the summed rectangle of the hero sprites for draw sorting and draw the individual parts in a set order? That is exactly what we were going to do. I don't know if you caught that before when I was saying now that we have the ability in the sorting thing to just say this thing sorts in front of this other thing, I probably will convert to using that. But at the moment, we haven't augmented the render system to know that. Meaning we don't have a way of actually sending that information down the pipeline. And in the past, we didn't have a way of acting on that information either, really. Although I guess we could have probably hacked it the same way by just saying, hey, sort this like virtual nub that's like a couple different bitmaps together, right? So we could do that. But no, that is exactly what I would like to do. We just haven't gotten there yet. FUCon, something exciting happening over at Molly Rocket. Sorry, not... What does that refer to? Dan020. Can using C programming optimize the game more than C++? You know... It's a tough question to answer because it depends on what you mean by optimize, right? In general, unless something very strange is going on, C is a subset of C++ to a certain extent. C99 does, I think, have some things that C++ doesn't have, though, oddly enough, but I don't think they're super optimization related, right? meaning there's a couple syntactic things or whatever. But, you know, C and C++, as far as optimization is concerned, in general, anything that you could have written in C, you can also write in C++ for the most part. There's very little outside of the Venn diagram there, right? So really, the reason that, you know, C is sometimes, or might, why you might perceive, or why one could maybe make a statement like C is can be optimized better than C++, or C is more optimized, is not because you couldn't have written the same program in C++. It's because C++ typically has a lot of features in it that encourage slow programming. And since C just doesn't have those features, the programmer is not going to accidentally use them, right? But if the programmer simply doesn't do those things that are slower in C++, then it's not like the language itself is somehow going to be slower, right? And so to elaborate that on that just a little bit is C++ has a number of features that are designed to sort of do a lot of things automatically, right? For example, constructors and operator overloading and implicit conversions that you can define, all these sorts of things. What that means is that any line of code in C++ might, although it looks very innocuous, might actually do hundreds of thousands of cycles worth of stuff. And so it's very easy for a C++ programmer to accidentally write code that is very slow without really thinking about it, because they just did a few little things, and they didn't realize this was going to call like 50 functions and do 20 different conversions and all this other stuff, right? So in that sense, C++ can be a lot slower, right? But it's only because you were using those features of C++. The language gave you the opportunity to do something slow, and you took it, right? But it's not like you couldn't have just written the equivalent C version still in C++, right? So for the most part, unless there's something that that's like slipping my mind, I can't think of anything inherently slower about C++ code than C code. It's just about whether you decide to use certain C++ features in ways that cause lethargy in the code, if that makes sense. Uplink Coder says RTTI. Well, RTTI doesn't affect your code at all if you don't use virtual types, right? I mean, runtime type information doesn't get added to C code written in C++. So it's exactly the same, I believe, as what I was just saying, is that you have to actually use these features in order for them to start costing you something, right? And the same is true of exceptions. If you never throw an exception, the compiler doesn't have to do any exception handling nonsense in your code. Now, granted, that stuff is kind of already in there now because Windows structured exception handling is usually in there and blah, blah, blah. So I think even C code now currently pays the cost of exception handling. So. All right. All right, folks. I'm going to wind it down. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. Tomorrow, we will go ahead and use our acceleration structure to see if we can't speed up that collision testing, well, overlap testing, I should say. But until then, if you want to follow along with the code at home, you can always pre-order the game on handmadehero.org. It comes with a source code if you want to play around with it. We also have forums. You can go to ask questions, a Patreon page if you want to support our video series, tweetbot that tweets the schedule at you if you are interested to know when we're going to be live, and an episode guide that you can use to catch up on old episodes. That is it for today. I will be back here tomorrow at 8 p.m. Pacific Daylight Time. Until then, have fun coding, and I will see you guys on the internet. Take it easy, everyone.